Technically, we're recording, and I'm recording to my own computer, so hopefully that will work fine. So hopefully we have you covered, Victor. Okay, I'm going to switch over to my tablet, and can everyone see my whiteboard? Yes. Okay, great. So we're gonna kind of do a little warm up of acceleration, velocity, position. You're gonna feel like you're back in physics. I think this is where most of us make most of our mistakes in dynamics, is all of the stuff that we kind of take for granted that we knew in physics. And so I figured let's start with the place that we all make the most mistakes. So I've got this problem and one other kinematics type problem for you this morning. Oop, waiting room. All right. Welcome, Hui.
Hello.
Hey, you missed kind of the course intro. We're getting ready to start on our first practice problem, and we're doing a revisiting acceleration, velocity, position in 1D, just to get ourselves kind of reacquainted with the time derivative relationships between those, since it's going to be a big part of what we do in the course. So we're actually working these, a lot of my Zoom problems I'm going to take straight from the textbook. So if you've already worked them, great. This is the Hibbler 14th edition, problem 1219. And it's kind of cool because this is exactly the type of thing you might want to lay out if you were designing a rail system, in which case you'd probably have two places you can put your train stations, and you might be looking at a lot of especially the metro rail electric motors can be programmed. So you might program, okay, we want so much acceleration for so much time, and then start decelerating over this many minutes so the train can run automatically. So that might be something that you would do these kind of preliminary calcs for, and then program it into a controller motor or a controller for your electric motor on the train. I think the BART in San Francisco runs automated that way, or has at some points in the past. So this isn't just a an ivory tower construct. So anyway, so we can kind of draw a little diagram of this. I'm going to draw like velocity versus time. So it starts at rest, we're told. So velocity is 0, train starting at the station, it's not moving, people get onto it. We accelerate at a ½ meter per second squared for 60 seconds. So some acceleration there. 60 seconds. And then the velocity is constant for 15 minutes. I should probably break the x-axis because 15 minutes is on a scale quite a bit more. 15 minutes is, I gotta grab my calculator. Maybe somebody can calculate that for me. I like to keep things in the same units. Minutes.
It is 90 seconds.
15 times, how many?
90.
90? It seems a little
Yeah,
short.
that's what oh, sorry, 90 times. How about?
Yeah, somewhere else. I'll grab it and confirm. Okay. Some point TBD, and that it decelerates a little faster.
900.
900. Okay, cool. Thanks. So plus 60, if I'm going to do this continuous, this would be 960. Thanks. I'll let other folks wield the calculators here. And that's T, station B. Yay, thank you. Thank you, Joseph. Okay, cool. So 60 seconds, I'm going to call this region A, the acceleration region, our constant velocity region, and then our decelerating region. And, you know, we could, this should start looking a little familiar to you who've done shear and bending moment diagrams. This is totally analogous to distributed load, shear force, and bending moment, by the way, except we're doing a time rather than an X. So I found it's easier to just calculate distance for each region and set things up with a start time that's appropriate to each region rather than working out time offsets for the start and stop. I found that's a really easy way to end up making a math error. So I'm just going to tally up each region like by itself and get the distance for it. And I'm going to grab my cheat notes here, make sure I'm not making a mistake. So I'm going to start in region A. And I got an acceleration, by the way, positive to the right, coordinate axes to the rescue. So acceleration region A, positive, 0.5 meters per second squared. Our velocity, whenever we're going forward, velocity at any time, by the way, this is constant. So our velocity at any time is 0.5 meters per second squared times t plus our initial velocity, which was? Correct. Started from rest. Okay. So our position within A at any time is integrate again. Plus, what's our constant of integration here? Position. Depends on what we decided to call this spot.
The XB,
Pardon?
the XB.
It's going to be the origin here for this region, which we're going to call x equals 0. So the train station at A is x equals 0. So our constant of integration to go from velocity to position within region A is still going to be 0 because it hadn't started like 100 feet out of the station, like maybe it got stuck and needed a tow. No, it kind of started at 0. So this is our position at at whatever time within this region where we were undergoing this acceleration. So we're told we got 60 seconds. And so we want to plop 60 seconds into each of these expressions and figure out how far we went and how fast we were going at the end of 60 seconds. So does anybody want to calculate that for me? We got 1. So 60 squared is what? 3,600 seconds squared divided by 2 or divided by 4. Yep, I'll buy it. So the train covers 900 meters coming up to speed. Okay, so in the constant velocity region, we're going VB is what we accelerated up to over in region A. It's 30 meters per second. It's constant, it's not changing. So the distance we cover in region B depends on how long we travel at that speed. So 300 meters per second times, I'm going to go back and index these, times the time we're in region B. So how long do we travel in region B? Henry had done it before, 900 seconds. 60 to 960. $15 minutes.
I think it's gonna be like 30 multiplied by 900, right?
Yep.
I think it's 2,700 thousand.
27,000. Yep. So that's XB at 900 seconds. Okay, region C. Acceleration in C is -1 meters per second squared. Constant. Velocity within region C at any time. -1 meters per second. T, first time derivative. What's our constant of integration this time? I'm going to call this TC. So we're going to say 900 seconds total elapsed. I'll say T sub C equals 0. V sub C initial. It's V sub C initial within region C here. Oh, initial velocity within region C. So when the train,
Is it gonna be 0, right?
oh, velocity. So the train's cooking along at 30 meters per second, and then the instant before they start to decelerate and go into this region C, what is the velocity that they're initially at right at this instant here? Yep, 30 meters per second, exactly. So if you think about it, the velocity within region C at any time, we've got this negative sign indicating that we're decelerating, right? Because positive is to the right. So when we were accelerating, we had a positive A. Now we're decelerating, so A is negative. So we can look at any time within this region C where we're going to say t equals 0 when we first put on the brakes, we've got a negative sign. So this first term's negative. The second term is constant. So our velocity is decreasing with time, which is what you expect when you're decelerating. So that's kind of a little check that, hey, did I get my initial velocity right? So the position within region C at any elapsed time will be negative 0.5 meters per second squared. I'll just put in our number, make it easier. So when t sub c is 0, that means I just entered this. I've said now I'm indexing 0 to the beginning of that section, not all the way back to the beginning. So the distance I will have traveled from this point forward towards station B, or where the train stops. If t sub c is 0, that means I'm still back here. So x sub c is 0. That makes sense. I'm also putting this as, so I'm breaking each region up so its initial conditions are kind of set at the beginning. Otherwise, these times would have to be subtracting the elapsed time to that starting point if I wanted a single continuous function for it, which is harder to deal with mathematically. It's possible, but you're riding along with those offsets that are specific to the different regions. So this is a little bit easier to look at. So what time are we concerned with within region C if we want to see how far we went? Until the train stops. Hint, until the train stops. Yep. So if you're looking at the chat, Joseph made a comment that at 30 seconds, the velocity is 0. And that's what we're concerned with. We want the train to stop at the station. So we go back to our velocity expression, say, hey, when is the velocity 0? Well, it's 0 at 30 seconds. Ah, okay. So let's plug that into our expression for position relative to wherever we were when we entered this decelerating zone, and get a value for x sub c at the time at which we will have stopped, and we'll then be at station B. So that's basically negative 0.5 meters per second squared times 30 seconds squared plus 30 meters per second times 30 seconds. All right. By the way, units check. We're getting answers in meters, which is good. And thank you, Joseph, for being our calculator. 450 meters total. So distance total. Distance traveled in A plus distance traveled in B so that would be your total interstation distance. I think it's kind of interesting that they're slowing down at twice, they're decelerating at twice the rate that they're accelerating. I don't know if that's jives with what the light rail does down in King County. You go flying across the train as you pull into the station. I haven't ridden Metro Rail in too long. Don't quite remember that.
I have a question,
You bet.
Professor. So can you explain again how you get TC, the time at point C?
Oh, okay. So we were concerned with within C, our time of interest when the train stops. We interpret train stopped. V sub C at a given time equals 0 is the same thing as the train stopped. So my expression for V sub C is -1 meters per second squared times the time from which I put the brakes on, which is T sub C, plus the velocity I was going at the time I put the brakes on, which is 30 meters per second. I want that all to equal 0.
That makes sense. Thank you.
Yay. All right. No worries. Okay. So has everybody gotten what's kind of step through what we did? So important takeaways: relationship between acceleration, velocity, and position in any coordinate system. I'm going to erase where we're going. So these are time derivatives, and that's something we're really going to be working with pretty much all the time. If somebody says take the derivative in this class, 9 times out of 10 they mean the time derivative. We'll do a few position with position or velocity with respect to displacement along a curve, but usually it's time. So if you've got, oh, I don't know, some coordinate system out there, Cartesian, I'm sorry, traditional, and you got some point P, and this would be true with any coordinate system. You can draw some radius vector from the origin to point P. That's like your position. So it's like X on the X-axis. In fact, there is, some X associated with that, right? It's right there. X in the I hat direction. Okay, so you got your radius vector is some function of time. Your velocity with respect to O, point P is flying along with some velocity. That's going to be the first time derivative of whatever your position function was. And if you want to know the acceleration, who knows what vector direction that's pointing? That'll depend on the sum of the forces that's acting on it. Acceleration is going to be the second time derivative. And in the train problem, we started with accelerations, which in dynamics, we're going to usually get, we're either going to be given or we're going to get them from the sum of the forces. So you're going to take your FBD, you're going to sum up all the forces in whatever directions you need, and you're going to figure out the mass that you're working with, divide that force sum by the mass, or divide the moment sum by the moment of inertia, and you're going to get an acceleration or a torque right there. Then you're going to integrate to get velocity, then you're going to integrate to get position. And each time you integrate, you're going to have a constant of integration that you have to know something about the problem to evaluate the constant. So to go from acceleration to velocity, you're going to need to know some kind of initial velocity, or the velocity at some point that you can use to evaluate that constant. And when you go from velocity to position, you're going to need to know some kind of initial position. So that's one of the reasons that we were saying we needed to know, say, where did you start? How fast were you going when you started? When we were in that region A with the train pulling out of the station, we had to integrate twice. We had acceleration. So it's like, okay, I got a V0. What was my starting velocity? Oh, I started at rest. It was 0. And now I need a starting position. Where did I start? Well, I'm going to call it station A 0. So I got a 0. Because we broke up our train movement into different regions, I started the time and the distance clock at 0 within each of those regions. And that helped me simplify my my initial conditions in all cases. Just as this is a real helpful exercise, you use this for shear and bending big time. And so I'm just gonna draw this for the problem that we just did. And now I'm winging it. I prepared everything else. So let's look at, let me move this over here a little bit. These can get, oops, no, just move this, please. Out of the way, okay. Shrink it and move out of my way. Well, we're gonna be obstinate. Yay, okay. So we started out with acceleration of 0.5 positive, and then it went to 0 for a long time. And then it was fairly big in the negative direction for some time. And then the train stopped. If we look at velocity as being the first time derivative of acceleration, we started from rest, so velocity was 0. And so we would expect to have some line function with a positive slope that's equal to our acceleration. Then we're going to have a constant velocity when acceleration is 0. And then we would expect, well, that can't go on for that long. Steeper velocity going to the end because we had that acceleration is the slope of the velocity here. So that can kind of keep you straight on what's increasing, what's decreasing. And if you ever have a problem where you're looking at pursuit or collisions of two things that are moving, and you might want to know, when do they hit? When do they overlap? What do I have to do to make sure they never coincide so their X values are never the same? Some plots like this can really help. And by the way, you can make plots in Excel for these time-based problems. So you can plot time and position with your equations, especially if you're in a region where your acceleration is continuous. But we could use the same kind of logic and say, okay, I'm going to take the first time integral of this sloped area here. That should give me a parabola. Again, we're starting at 0. So we're going to have something that's concave up. Then V is constant, so we should have something linear. And then we should have something that's concave down, but still increasing to get to our final position. So you could write the equations. And then line equations, and then parabolas, and actually plot that, use that as input to a spreadsheet or any kind of solver program that you might be using, and make some plots. So if you maybe had another, another function, I don't know, maybe it got started later, but it accelerated more, and maybe it started out here and it had a huge acceleration, and then for a while and then stopped. You could basically say, okay, it starts out here and it's got a real steep line, and then velocity levels off, whatever, and you could they crashed here. So you can use your acceleration velocity position plots to kind of get a time-based graphical image of your equations of motion. And by the way, when we say equations of motion, these are what we're talking about: acceleration, velocity, and position versus time, otherwise known as parametric equations. If you're used to that, everything is a function of the same parameter. So is that kind of ringing some bells for those of you who've taken statics and recently? Looking kind of familiar? Is it looking, is it not looking familiar? We'll ask that. You're in big silence. Yes, exactly. Exactly, Joseph. Looks like bend and shearing. Perfect. Okay. So basically this is, again, we're doing some basic physics, but trying to put some twists on it that are going to make it a little bit more universal. Get rid of that. Okay, let's try another problem. This is another one out of the textbook. This is Hibbler 1213. So now we got two vehicles. So this is stopping distance, and this is very important for traffic design. By the way, one of the main applications for dynamics, in addition to machine design, is traffic. So road layout. The equations of motion are very, very useful for designing roads, minimum radii of curvature, minimum radii of curvature on horizontal and vertical sections, banking angles, pavement types, safe speeds that become part of the code, the legal code. A safe highway design is based on equations of motion along with average vehicle masses, average coefficients of friction, etc. And then, of course, engineers are frequently constrained by geology and geography and cities and where you can put roads. Plus we want to get people where they're going to go as fast as possible without having them flying off the road. So dynamics, the type of kinematics and kinetics are used constantly in deciding what is and isn't a safe road design, or in applying it. So this is a small example of that I'm sure you saw in driver's ed somewhere. So you've got, I'll try to set this up again with our, just draw a little sketch. So you've got, you know, a vehicle and it's heading along at 44 feet per second. It can, oop. I didn't type up the question, but I'm just kind of verbalizing it. So I'm setting up the scenario, which will be the question. So you got a car, it's driving along with a constant velocity. It's capable, the braking system in the car and the pavement friction and everything is capable of providing a deceleration. So I'm using signs now. So I'm gonna designate positive acceleration, velocity, and position is to the right. So we can decelerate at 2 feet per second squared. If you've got some person standing out here and you don't want to hit them, you don't want the position of your person, the position of the car to be the same ever, unless the car's velocity is 0. So we can express those mathematically. A normal person, from the time they see an obstacle, will have 0.75 seconds delay before they can initiate that deceleration. So that's something else that's used in highway design is sight lines. You know, it's used especially for maximum slopes. When can you see, at what point in the curve and the hill, if you're coming up one side, at what point will you be able to look ahead and see somebody that might be out of their lane, that's in your lane? And that's used to basically set maximum speeds versus slopes versus hill profiles. So radius of curvature of the hill will determine sight lines, the average, you know, distance a person can see. So those are all, you know, those are all things that we'll start to tackle with like tangent normal systems and maybe a function for what your line of sight is. This is real simple though. I'm trying to give you some views ahead of where you would apply these types of things. But today's examples are all 1D, really simple, just getting used to framing kinematics problems. So definitely won't be doing all of this like this week. Anyway, but this we can do. So you're driving along, you see somebody walks out on the road, or a dog runs across the road or something like that, and you don't want to hit them. You've got this reaction time. Your car can apply this kind of deceleration. How far apart, how far ahead of this obstacle did you need to be to avoid hitting them? How would we set that up? We can kind of do another one of these little. So at first your acceleration is going to be like 0. Then you're going to apply your negative 2 feet per second squared. You started out with 44 feet per second velocity, and it stayed constant until you hit the brakes. Acceleration 0, velocity is constant. Then you had a constant deceleration, which means your velocity was coming down. And we'll assume it hit 0 at this point here. You stopped. Your distance, your x, you started, we'll call this, 0 point. Looking at the board a lot, so if you have a question, yell. So constant velocity, the distance you've covered towards your person is going to be linearly increasing. Now you've got a negative slope on your velocity, so you're gonna stop covering distance so fast. So you're gonna have some kind of parabolic function concave down, but you're still covering distance during the deceleration. So you could kind of break your distance up as kind of what you covered here in your, call it the reaction time, and then the distance you covered during your deceleration time. So this is your X reaction. And that's your X decel. And there's your X total. And your X total better be less than however far apart that person was from you, or you will not be at 0 velocity when you overlap them. And someone will get hurt, and then someone will get sued, which is very bad. We don't want either one of those. So an easy way to do this, again, without having to do time offsets within a single continuous function, accounting for this lag time, and when you applied the brakes, I think is, again, to break up our distance into two time periods under which we kind of had a different set of equations applying. And these equations of motion are what we would call piecewise continuous. So over each different region, we got a continuous function. It's got to be continuous. We're taking like integrals and derivatives all over the place, right? Then we've got a discontinuity where something's changing, level, it's changing slope, or it's changing curvature. And then we got another region. So I find it simpler to use the tally up and to keep things straight, and then start a 0 point at the next region. That's kind of the way I did my shear and bending along beams. If you want to create a continuous function with time, you can. It works just as well. You can work the problem both ways. I found, again, it's a little harder to keep up with those initial conditions in those cases. So there's always more than one way to do it right. There's usually 2 or 3 ways to do it wrong. A lot of ways to do it right. So if you want to work at your own pace, I'm going to go through this and maybe ask for some calculation help, so I don't have all the numbers written in my notes. And then we'll repeat this for a drunk person who puts on their brakes later. And I will add sleepy. That, I think, creates an even longer delay. So I'm going to do the reaction zone, where we are reacting to the site of the person. A equals 0. We'll call it TR for T reaction, equals our initial velocity of 44 feet per second. And the time we travel from within that region is, of course, 44 feet per second times time. And TR ends at 0.75 seconds. So how far did we go? Does anybody have a calc there? 44 feet per second, 3/4 of it,
33.
33 feet. Cool. Okay, so that's this point. Okay, so now we're going to go into the deceleration zone, decel zone. Now A equals blissfully -2 feet per second squared. Our velocity, we'll call it TD for T deceleration. We're going to integrate. And we're going to add our initial velocity when we entered the deceleration zone was 44 feet per second because we hadn't started decelerating at that point. Oops. And our position, I'm going to call this again. I'm going to call it TD equals 0, XD equals 0. I'm breaking it up, creating a new little set of initial conditions there. So I'm going to integrate again. If I were indexing all the way back from the start where the driver first saw the person, I would add this 33 feet in, but I'm breaking the problem up into zones and then I'm going to add the distance. So I've already established when T sub D deceleration time is 0, my distance covered within the deceleration zone is 0. So when T sub D is 0, X sub D is 0. Again, this is the breaking it up part. So I should be saying, I should index everything by zone. It's the zone specific method as opposed to the continuous over the whole problem method. It should be T sub D. That's really important not to get sloppy here. Okay, so let's see, how long do I stay in the deceleration zone? How long do I decelerate?
16.5.
16.5 seconds. Well, what happened? Oh, we got another vote of 22 seconds. What happened to conclude my time of deceleration? Yeah, I stopped. So what I'm going to do is, again, where does this equal 0? More importantly, I'm sorry, when does that equal 0?
I'm sorry, it's 32. My bad.
Yeah, 22. It's 22. So we solve this equation when it equals 0. So we set this equal to 0. 44 goes to the other side with a negative. We divide it by -2 and we get time, deceleration time equal 22 seconds. So we stop when time from the onset of deceleration is 22 seconds. Okay, so all we have to do is pop that into here. to figure out how far we traveled in this deceleration duration. So the distance covered while we were decelerating, when the time from start of deceleration is 22 seconds, is -1 foot per second squared times 22 seconds squared plus 44 feet per second, which was our velocity at the time that we started decelerating, times 22 seconds. Quick unit check. Seconds cancel, gives me feet. Second will square here and cancel. So I'm going to get a distance in feet. Never neglect those unit checks. Anybody want to calc this one? I may have this one. I think I got 484 when I calced it the other day. Yep. Okay, good. We got consensus. So from the time you start decelerating, you travel 484 feet. So really, when you look at these two, this is not drawn very well. Oh, well, it's drawn really well. It's not drawn to scale. Go ahead.
So what is the time? I mean, the deceleration is -1 over here.
Yeah. The deceleration is -2 feet per second. But when we integrated this expression with respect to time, right? To go to position, we have a constant times t. So to integrate this with respect to time, we would get a t squared and then a 1/2 in the front. So when we take the derivative, the 2 would come down and cancel with the 1/2, we'd end up with t. So the 1/2 is where we have the -1 instead of the -2.
Thank you.
No worries, we got there. So really, this region is huge, 484 feet compared to this one. It's only 33. So if you're normal, you have normal reaction time, the majority of the distance you would cover in stopping is limited by your car's braking system and the friction of the road. So if you're a highway designer, you're going to assume the average person, or maybe the slowest person, like my reaction times, I'm in my mid-50s. Mine would definitely be slower than most of yours, presuming most of you are in your 20s. That's a biological reality. And when you design roads, you'll design for probably the slowest driver. As you're designing across the spectrum, you don't want any accidents. What happens that really makes it difficult for highway designers, and it's why we have driving laws, is if we alter our consciousness with sleep deprivation, especially being one of the most effective ways of decreasing our reaction time, we'll start to change this number. And so in the book, they cite someone who has an alcohol blood level above the legal limit as going from that 3/4 of a second reaction time to 3 seconds. So the highway designers, let me just erase all of this and draw it back to scale, because this is kind of significant when we think about a design application. So where is the majority of that distance, that d, between you and, I don't know, the person who's standing in the road who can't get out of the way, or an obstacle in the road? You're driving through fog and all of a sudden you see an obstacle. How are you even able to stop in time to hit it? Maybe. So here you are. I'm just going to draw, X versus time. So here's your reaction time, and here's where you dang well better be stopped. So we were looking at something where we're traveling, you know, like this maybe, and then the majority of the time of the distance traveled is during the deceleration itself, with proportionally very little of it being in this time that is the delayed while you're getting your foot onto the brake or whatever you need to do. X reaction, X deceleration. If you're going to design a road, you're gonna have some measure of this based on human physiology, all kinds of driving studies and things like that, where the average human, maybe the oldest person who is likely to be driving would be granted a driver's license. You'll design around this, and then you'll design the road partially to control this. This is driver controlled, human controlled. This is going to be a function of vehicle and the road surface. So if you're an automotive designer, you can control this, you can't control that. If you're a civil engineer or a highway engineer, there's some stuff you can do to that road surface to increase the coefficient of friction and whatnot, increase road drainage that's going to maximize this deceleration that can be applied. So, you know, your vehicle manufacturer, you're going to design a better braking system, like anti-lock brakes is one example of vehicle design that increases this. Road surfaces, rougher road surfaces, better draining road surfaces, things that won't have standing water, surfaces that are not prone to icing. Highway maintenance, these are all things you can do to increase A. Highway engineers, vehicle engineers can't change the driver. There's nothing you can do to change this stopping distance, this portion of the stopping distance. You can design around this part only. You can make that basically as small as possible so that anybody, you know, so that this person can be closer and you can still stop without hitting them. Nothing you can do about this. What changes this is law and law enforcement. Unfortunately, you're talking about a social change, human behavior here. So let's do kind of as a final exercise today. Let's look at the magnitude of that human factor, that uncontrollable one. And by the way, these types of human factors, human versus things that we can know and measure and be sure of, when you run into assignment of safety factors, this kind of human factor is something that would be, if you were designing structural things, you would call that a live load, because it's something that you need a lot more understanding of. It can change without you meaning to change it. So dead loads are things like weight or very measurable wind strength. Live loads are things like traffic. Somebody could suddenly start driving something way heavier than you ever thought somebody would drive over your bridge. You put bigger safety factors on things you're less sure of. So somebody impairing themselves to the point where they can't drive their vehicle is a huge uncontrolled factor. And the respect for that is probably one of the reasons why impaired driving has such a heavy legal penalty, because of these consequences that we engineers can't really do a lot about. So let's walk through our book and kind of get an idea of what design penalty this impairment of 3 seconds. And I won't draw the graph this time. I'll kind of sketch it at the end. So we got sleepy driver. Sleepy driver would probably be more like 4 seconds. We'll do the 3 seconds so we can check ourselves with the book. So we have drunk driver. Whole scenario is the same. They see the person out in front of them. They're not blind drunk. Their eyesight's still okay. So they're still stopping, you know, seeing that person with distance d between them and the person. Their car can still decelerate at 2 feet per second squared. The road's the same. The only thing that's different is their reaction time. So during their reaction time, acceleration 0. Their velocity, they're driving at the same speed. Thank goodness they weren't speeding. That would have been worse. We just used a different velocity to start. But their velocity during the reaction period is 44 feet per second. What they came in with, we're assuming they're starting at the same speed as the non-drunk person. If we took the first time derivative of 0, we'd get a constant. That constant happens to be 44 feet per second. And the distance that we are going to go during our reaction time is going to be a function of time. $120 plus 12, 132. Yay. Okay, so this is the distance traveled during the reaction time for the drunk driver. This is versus 33 feet for the non-impaired. Now, remembering that the deceleration distance, get that spelled right, decel. Just because I'm shortening it doesn't mean it shouldn't be spelled right. The deceleration distance for the normal guy, gal, driver, was 484 feet. What's the deceleration distance for the drunk going to be? Quick. And don't have to calculate it.
I think it's gonna be more than the normal guy.
Actually, it's going to be the same, because the only difference in between the drunk and the normal driver is when they applied the brakes. From the time they apply the brakes, that whole deceleration curve is the same. Let's prove it. We use different color. Green. So I'm going to say a decel for the drunk, -2 feet per second squared. The velocity during deceleration from the time we start decelerating, it's -2 feet per second squared times the time from when we put the brakes on, and x decel. We're going to take the time derivative plus initial velocity of 44 feet per second. Because we weren't decelerating during the reaction time. So now we take the first time derivative, -1 foot per second squared, GD squared. So we get the same exact expression for equations of motion during deceleration, regardless of what time we started that deceleration. This guy started later. But once he hit the brakes, his equation of motion was the same as for the person who started earlier. Because once they hit the brakes, they're not in control anymore. Now everything is controlled by this value. Now the vehicle and highway engineering takes over, and you know, it's out of the hands of the driver. You're going to stop as soon as you can stop, and it's going to be controlled by that A, which will in turn be controlled by the vehicle and the highway. The significant thing is you covered almost 100 additional feet because you couldn't hit the brake fast enough. So if the normal person would stop maybe just short, maybe, you know, 10 foot short of the person, the drunk would hit them and still, neglecting conservation of momentum, would hit the person and still travel another 122 feet. There's no way they could avoid hitting him. So the key thing is this human factor, which we can't control as engineers, blew the acceleration component out of the water. Or at least it was a significant fraction of. So we had 33 feet of travel during the reaction time to hit the brake versus 484 feet during the deceleration for the normal person. I'll put the drunk in red, versus 132 feet for reaction time, and then another 484 feet just to stop. So 33. Oh, sorry. Go ahead.
So let's say that in the scenario where the reaction time are really different, and then they hit the person, is it gonna have the same momentum or not? Because I don't think so.
Momentum will be
Different, right?
Yep.
Yeah.
Momentum is kind of skipping ahead.
MV, yeah.
Right. So we would go back to we'd look at our velocity at find the distance, where the distance is d, find the time, find the velocity, and we'd work the problem backwards to velocity in each case to figure out what the momentum was, which then we could use to, if we knew the time of the impact, we could get the force applied to the person, which is probably going to be just really scary big.
Yeah, because I just don't get it, like why we should not include the reaction time on that calculation.
Oh, which one?
Like on both of them, you say like to find the distance between the car and the person, you don't have to include the reaction time. Like for example, those 33 and 132. You say we should not include that.
Oh, you're talking about not including the reaction time down here?
Yeah, that's what I'm saying.
Because this is a completely different part of the problem. You know, it has to do with the way that I chose to set it up. So basically, I took the car. I mean, you could set it up differently. The car is going along and it goes, you know, a certain distance before you hit the brakes. Brakes hit. And then it continues to travel while it's slowing down. We've got a different equation of motion that applies during this period than during this.
And then you say we can add them up like to have like a total distance.
Total distance. Yep. If you consider them separately, then you have to add up. So I could put over here X total. So in this case would be what? 7. I think I've got them added up over here. 517 feet. Let me write that a little neater. Yeah, maybe that's confusing. Let's write the totals. So we have 517 feet total there, and 616 here.
Yep.
But that difference in the total distance was solely due to this portion of the motion.
Yeah, that's the one that makes a difference.
Yeah, this is where the difference is coming. So this is human factor controlled, human, and this is vehicle design, highway design controlled. So from a driver's standpoint, this is all you can control is your reaction time, your alertness, your whatever factors into that, because your vehicle's engineers, the state of your vehicle, your tires, and the highway has already determined this. You can't control this. If you're a highway engineer, this is all you can control. So understanding dynamics in these two scenarios, as engineers, it tells us, hey, what can we control? What do we have to assume? And, maybe we need to put a few more safety factors and make this smaller to account for the fact that we're going to design our roads to be safe for drunks. We're going to basically say, okay, the speed limit's going down because we're going to assume, this reaction time of 3 seconds, and we know what distance you can see ahead of you on this roadway, because maybe it's hilly, whatever, you're coming out of the hill, your line of sight is going to go into the hill. Here's your D. If we know the human reaction time we're going to design around, we know what acceleration is possible given friction, tire characteristics, vehicle braking characteristics, then we can recommend a safe speed using these same equations. So we can work the problem from different aspects depending on who we are. But so a little driving safety and highway engineering example, and to make our review of 1D kinematics a little more interesting there. But did everybody understand, again, our derivative relationships, equations of motion applying over different regions where we had different acceleration conditions for our starting? Okay, yay. To me, it's those ending points that always make it, the hardest is, okay. What was my initial condition? Okay. Any questions at this point so far? We've got enough time to maybe do another quick problem, or is that if anyone has started the quizzes or anything like that and wants has run into questions, we could take time for that. Is anybody having trouble getting together with your teammates? That's another new twist this quarter. All of those, the homework, the 40% of your grade, the big complicated homework exercises, they're teams. So you'll be great. Everybody on the team gets the same grade. So it's like you're a little startup company producing a demo product in the form of your homework submission. So you want to get a lot of money in the form of a lot of points. Okay, no worries. We got one person that needs to cruise. We can end now. We can do another problem if anyone wants. But Celia, before you leave, just checking in, have you been able to make contact with your teammates, your homework teammates? You good? Not seeing anything. Okay, that's super priority number one, because it really, really helps to work these as a team. You will do much better. Even if you break up the problems and each person do a few, change them and check each other's work. So this is some good practice working on an engineering team, very, very similar to what you're going to do, even if you work for a big company in a division. And you can, I don't know what Highline's Zoom capabilities are, availability for students. I have, however long that I can have a Zoom account that I can work for an hour or two, whatever, with you all. Private Zoom accounts, if you remember from Statics working with me, I think you're limited to something like 40 minutes if you have more than 3 people. So your homework teams are only 2 or 3 people at most. So I think even a private Zoom, you should be able to get on Zoom and work together all day if you want. So even if you can't get together, you have to work alternate shifts. There's lots of tools that you can do homework. And when you go to work, you might be working problems like this on a shared computer system around the globe. So I figure this is good practice. Okay, wasn't hearing any cries. We could do one other kinematics. We can do a 2D. What do we want to do in 20 minutes? Tell you what, I'm going to set up one more of these and then, oh, that's too long. Let's take a look at our J-hat coordinate, which, oh, go ahead.
Sorry. So
No,
I
please.
also have a question on quiz 1. Like, can you do like an example of the first derivative of the dot product?
Oh yeah. Yeah,
Please.
let's do that. Okay, so let's grab some vectors. So I got vector A dot vector B. Okay, I'm going to grab my notes and read right from them just to make sure. People who come to Zooms, you get first dibs on asking questions. And Henry, this is definitely in my notes. So this is something to look for on the Canvas page under notes and instructor lectures. So this is literally on the first page. Just making sure. So the idea is a vector product is a product, right? So if I'm going to take the time derivative of this expression, I'm going to apply, basically the derivative of u times v is the derivative of u with respect to whatever times v plus the derivative of v with respect to whatever times u. So I'm just going to apply this to the dot product. I'm going to say, fine, I'm going to take So does that make sense?
It does. It's just formula.
Okay. So this is going to end up giving us, woo, what kind of product? These are both vectors. So this is going to end up giving us a scalar because we've got the dot products in here. If this were a cross product, which we'd honestly will run into with torque, angular momentum a little bit. We won't see this. We'll see this when we're looking at relationships between 2 points on a rigid body and position versus the body's own angular velocity or momentum. We'll end up getting into a lot of cross products. So you'll calculate that a lot, and you will take the first derivative of that. So when you're looking at 2 points on a rigid body, you'll get a lot of cross products. Trying to think where we run into this. So order matters on the cross product. So we'll want to keep A and B in the same position. So we can do dA dt cross B plus A cross dB dt. And so, you know, A keep it 2D. So the time derivative of each of these is going to depend on the time dependence of our coefficients of our coordinate system unit vectors. So it depends on how those depend on time. So, you know, this will be, so I can say, can write that as the first time derivative of vector A with, well, first time derivative is with respect to time, duh. dAx dt, whatever that ends up being, pointing in the I hat direction, plus the first time derivative of ay with, I'm not going to say that tautology, pointing in the j hat direction. So here's where you're going to apply your calculus. Depend on what these are. So you'll basically just have a different multiplier versus what you started with. This will end up being a different expression that you'll then operate on with your dot or cross product the way you would any other vector. Does that kind of point you in the right direction?
Yep.
Sweet.
Thank you.
Okay, yay. Okay, 20 minutes left. We can do, I got a long problem and a short problem. We can do another demo problem, or I can let you go early or answer any other questions. We've been going for quite a while, so what's the consensus? Do one more, or you want to quit? I'm fine with anything. Let's do a quickie little 2D. Let's see where I dredged that up. This looks small. It only took like one paragraph on my notes page. So this was, where did I get this? I feel like our J hat, our Y axis, has been a little neglected so far. So I'm looking for something that's got another dimension to it, just to round us out. There's a figure here. This was kind of apropos of Henry's question. See if I can do this without getting too rushed. And if I am, I'll just continue at some other time. So this is Hibbler problem 1285. So a helicopter takes off from this point on the ground, and it's gonna fly up in the air like this. So this is literally X is horizontal displacement and Y is vertical displacement. And we got a set of parametric equations. So our X displacement from, or our X position at any time actually, which is the same as displacement because we started, you know, at the origin. A is the origin. It's not always the case, but we've got a 2 t squared, and that'll be in meters. And our vertical with at any time is 0.04 t to the third meters. And someone wants to know, oh, t's in seconds. Someone wants to know how far the helicopter has gone from point A and what its velocity and acceleration are at 10 seconds. So here's another twist on position, velocity, acceleration. So how would I describe the position at any time? As they said, the distance from point A, they didn't ask the total distance traveled. So we're not going to have to integrate its path. I just want to know how far you are from point A.
I think you got to walk to with each axis.
Got it. So I'm going to make myself, I'm going to use another color. I'm going to make myself a radius vector, which is going to have components RA to the helicopter. And it'll have a component going on each axis. So we can use our handy dandy properties of vectors. We won't plug in all the numbers, we'll just write the equations. So there's our distance, our straight line distance. Call it straight line distance. Why would we care about the straight line distance? Maybe we have to send an optical or a radio signal, and the things like VHF tend to go on a line of sight. It's just a problem somebody made up. Let's see. Velocity expression. How do I get velocity from position? I vote take the first time derivative. Hey, I got an expression in terms of time. How handy. So I'm going to have 4t in the I hat direction plus 0.12 t squared in the j hat direction. And I could, of course, get the total magnitude of that velocity by applying Pythagorean to the two subcomponents. There's the magnitude of my velocity, otherwise known as my speed, and that will be directed, oddly enough, it's going to be heading tangent to that path. That's one nice thing about the velocity vector. If you know something about your path, which you will if you're given parametric equations for two different coordinate directions in any coordinate system, Know that your velocity vector is always going to be tangent to your path. Your acceleration vector, heavens knows what direction it's pointing it. Probably isn't more times than not. So, you know, but velocity is always tangent to the path, and can't think of any case it's not. So that's something you can leverage to find other things as you need to. And I think it's the subject of a couple of problems you can practice with. So let's see. Do you think the acceleration is going to be constant in the x direction? Show of hands, who thinks it's constant? I do. Okay, so the acceleration with reference to point A of our helicopter, we're going to take another time derivative. D dt, d dt. We're going to end up with 4 I hat plus 0.24 t j hat, and we can do the same deal. Poor Victor, you keep getting bounced out. I think someone's having some internet problems. It's okay. So we can do the same. Just write that 4 squared 0.24 t squared. There's the magnitude of our acceleration. So we can determine the magnitude of the displacement, the straight line distance, the velocity, and the acceleration anytime. Just plug in whatever time you want for t, and you can figure that out for whenever in the helicopter's flight. You can also extend the path with time and see where they're going to go. And you can even notice the relative direction of these two at any given time and say, hey, you know, which direction is the acceleration pointing? In a lot of cases, it'll be normal to the velocity. In some cases, it'll be parallel to it, depending on what forces are operating. Forces set the acceleration. Good little review of vectors being applied to a semi-practical case. Yay. Okay, I think we're good for today. Some good examples, good topics, good participation, guys. Thanks so much for coming to morning Zoom. We'll continue particle kinematics for the next 3 Zooms. We spend 2 weeks on that. You actually get 3 quizzes. I'll stop sharing so I can talk to everybody. I think you got 3 quizzes and a big homework. I think there's a lot of questions on it. I'll try to do more 2D in the next one, and then pull in cylindrical tan normal coordinates and start looking at things like unit vector directions versus the change in the unit vector direction with time or something else, and working out, and this is definitely look to my notes for that. There's a little bit more richness there than in Hibbler. Looking at working out our position, velocity, acceleration expressions for cylindrical and tan normal. I'm just getting a little idea of, okay, why is this pointed this way? And then how did our just rules of taking derivatives plus rules for how our unit vectors change when we make a change with time, and then get a picture of how we can express things in different coordinate systems and then use them for something with different things being held constant. So wait, by the way, the difference, having different coordinate system is not intended, the whole purpose is not to make our lives miserable as dynamics students, but to be useful for things. So cylindrical and tan normal, axisymmetric, and things like traveling. So future highway engineers, you like tan normal because you're going to measure things with respect to one place along a road or a path. Mechanical engineers, you're going to work with a lot of rotating stuff. So You know, cylindrical coordinates are like there for anything axisymmetric. Let's see, bookstore, book of the bookstore. Eek. It should be. If you haven't, if it isn't available, let me know. It is listed in for the course is required. So if you need to rent it again or check it out again, it should be available for you to purchase another time increment. Let me know if it's not. There are a few kind of like spare bits of things that I can loan out on a limited basis. If you can't get your hands on the book in the next day or two, let me know. But it should be there. Yeah. Our book is copyrighted, so we got to be pretty respectful of the publisher. But that said, you know, I'm definitely willing to get some stuff to you so you can keep your learning. And in the meantime, start with my notes. There's a lot of overlap between the two at this point. Awesome. All right. I'll see you guys on Wednesday morning. Thanks so much for coming.
Thank you.